In this first video, in the video series on chemical reactions, I'm going to introduce the concepts of physical change, chemical change, and the basics of what makes up a chemical reaction. So to start off with, let's look at the definition of what physical changes are. So physical changes are processes that affect the form of a substance, but not its chemical composition. So in other words, no new substance is formed. And that is critical. So the substance will change even in the way you see it. It may go from being a liquid to a gas, for instance, water being heated to the point where it boils and changes into steam. There is a definite change in the state or the phase of the substance. But the substance still, on a molecular level, still remains the same substance. So in the case of ice melting to water changing into steam as it is continually heated, the phases change, but the substance is still on a molecular level is water, H2O. So examples of physical changes are, for instance, phase changes, as I've referred to, the breaking of glass, the cracking of an egg, the mixing of sand and water, and there are many, many, many more. On the other hand, a chemical change is a process where one or more substances are altered into one or more new and different substances. So what is critically important here is that there is a rearrangement of atoms on an atomic level. And most physical changes can be reversed. For example, if we melt ice, then we can then also freeze it. So we reverse the process where melting takes ice from solid to liquid. Freezing will take the same substance back from liquid to solid. But many chemical changes are not reversible. For instance, if we take a piece of charcoal and we burn it and react it with oxygen, then it forms carbon dioxide and a large amount of energy is released. It is impossible for us to reverse that back to the oxygen gas and to the piece of charcoal, which is carbon. So when chemical changes occur, there is also normally a significant change in the energy of the system. And we'll learn a little bit more about this later on, but most chemical changes actually give off a significant amount of energy, or they take in a significant amount of energy. So here are a few examples of chemical changes. For instance, baking soda and vinegar will give off bubbles of carbon dioxide. When we react an acid with a base, when cooking an egg, burning a candle, when iron rusts, the digestion of food in our stomachs, the pouring of peroxide on a wound in order to ensure that the wound is clean, these are all chemical changes. So it's important also to be able to identify or to recognize a chemical change when it is taking place. So there are some indicators that we can use in order to identify whether a chemical reaction is taking place or not. And they are highlighted here in bold. So the first one is a temperature change. When we put a thermometer in the vicinity of substances that are reacting, we will find that there will be a change in the temperature. Light, very often light is given off. For instance, when you strike a match, that is a chemical reaction, and we see that energy is given off in the form of light. Bubbles often show us that there is a gas that is being produced as a product, and if it's being done in the context or in the vicinity of a liquid, then the gas forms bubbles which we can see. The formation of a precipitate, that normally happens when a solid product is produced in a liquid environment and the solid product doesn't dissolve and remains in suspension, and so we see it as a precipitate. Color changes often show us that there is a change in the substance because different substances manifest different colors. So if there's a change in the substance, you might find that, for instance, the solution changes from, for instance, pink to colorless, or from pink to blue. And there are many different color changes because there are millions of different types of chemical reactions. There can be an odor change. For instance, if I take sulfur and then I react it with oxygen, it will produce a very acidic sulfur dioxide gas, and that we'll be able to pick up as a very sharp, pungent gas that will, when it goes into your nostrils, it will burn your nostrils. And then many chemical reactions are actually irreversible. I need to say that there are reactions that are reversible, but then you need to close the environment. In other words, you then seal off where the reaction is taking place, and you don't allow the products to escape, and so you allow them to react with each other. And with certain chemical reactions, they can be reversible, but in day-to-day life, most chemical reactions we experience as irreversible. So how do we represent chemical reactions or chemical changes in a formal way? Well, what we do is we start off with substances that we call reactants or reagents. The word reagent is often used, and it can lead to confusion, but both words mean the same thing. They are the initial substances that you start off with before the chemical reaction actually takes place. Then the chemical reaction takes place, and there are certain things that are needed in order to start the chemical reaction. Very often it's a certain amount of energy. For instance, if you are brining at home and you want to light the charcoal, you need to use fire lighters, you need to strike a match, you need to put heat energy in to the system so that the fire lighters catch a light and they give off more energy, and then they give enough energy for the carbon in the charcoal to react with the oxygen. So we're going to learn a little bit about the chemical kinetics or the chemistry of chemical reactions a little bit later on in this series on chemical reactions. We're not going to go into too much detail on grade 8 level, but we will be going into a lot of detail later on in the science offering when you get to grade 10, 11 and 12. So you start off with reagents or reactants. The chemical reaction takes place. We represent the change by an arrow, and then finally the products are produced, and the products are the substances that are left over after the chemical reaction has taken place. So on grade 8 level, we are going to represent chemical change by stating the reactants, the change being represented by the arrow, and the final state of the system, or the final substances that are left over after the chemical reaction has taken place, will be referred to as products. So let's look at an example. So the first example we're going to look at is that of hydrogen and oxygen gas reacting. Now this reaction is actually extremely explosive and is used in getting rockets to actually go into space. So they actually use the energy that is produced by liquid hydrogen and liquid oxygen actually being allowed to react in the combustion engines of rockets. And so, for instance, like SpaceX and NASA, they make use of these gases in order to propel rockets into outer space. They produce water, but that's not the real reason why they carry out the reaction. The real reason is that they want to get a lot of energy out. So the reactants are the initial substances, and they are the hydrogen and the oxygen gas, and then they are initiated or they are reacted by a, if you want to call it a spark, a certain amount of energy, and then the reaction takes place and it produces a product in the form of water. And we can add here, we'll look at energy at a later stage, and a lot of energy in the form of heat and light. Now, that's the word equation. We then represent the chemical reaction in the form of symbols. So the chemical equation, or we can also refer to it as the symbolic equation, the chemical symbol equation or the symbolic equation, we write as follows. We write it as 2H2, because hydrogen occurs naturally as a hydrogen molecule, H2, plus O2, then produces water, which is H2O. Now, we are not going to expect you to learn these reactions off by heart. And neither are we going to expect you to produce these numbers in the equation. Producing these numbers is referred to as balancing the chemical equation. That is something that you are going to spend quite a bit of time on in grade 9. But for the time being, we are going to just give you the equations, and then we are going to ask you to, for instance, produce the particle diagram for a particular equation. So in essence, we want you to learn about reactants, about products, and about the different forms that we use in order to represent chemical change, namely word equations, chemical symbol equations, and particle diagrams. So for instance, in this case, in this example, 2H2 means that there needs to be 2 hydrogen molecules that will need to react with 1 oxygen molecule, and by reaction we mean that they have to collide, they have to bang into each other with a high enough speed in order to be able to break apart, and then they reform to produce molecules that consist of a single oxygen and 2 hydrogens, and there will need to be 2 of them. Now, there's a lot that's actually lying underneath this, which we are not going to spend too much time on. But one of the fundamental principles of chemistry and physics is that matter is conserved and that atoms are conserved. So if you have 4 hydrogen atoms on the left-hand side of the equation, on the reactant side, and you have 2 oxygen atoms on the left-hand side, then on the right-hand side, when the chemical reaction is finished, even though the atoms have now recombined into molecules that have a different structure, if you count the number of individual types of atoms, you see that the number of atoms is conserved. For instance, 4 hydrogen atoms on the left, there are 4 hydrogen atoms on the right. 2 oxygen atoms on the left, 2 oxygen atoms on the right. And so this fundamental principle of conservation, or in other words, the fact that a particular thing remains constant throughout the process from beginning to end, in this case its mass and the actual atoms. This fundamental principle of conservation of atoms then requires that as we go forward with more complex chemical reactions, that we need to balance them when we represent them. But as I've already mentioned, that is not the focus of grade 8, but that is the focus of chemical reactions, or one of the focuses of chemical reactions in grade 9. So to re-emphasize, in any chemical reaction, the total mass is conserved. In other words, the mass of the substances in the beginning will equal the mass of the substances at the end. And by the way, I need to mention this. When we refer to these numbers of molecules, we are referring to the ratio of 2 hydrogen molecules must react with 1 oxygen. But that doesn't mean that there are only 2 hydrogens and 1 oxygen molecule in the system. There will be billions and maybe trillions and quadrillions of hydrogen and oxygen atoms in a particular system when a reaction takes place. But the way they react will always be 2 hydrogens to 1 oxygen. And there's a really interesting experimental way of proving this in a lab. And then the second thing is that the number of atoms does not change. So irrespective of how the structure of the molecules change, the number of atoms doesn't change. We can see that the total number of atoms doesn't change. 1, 2, 3, 4, 5, 6 on the left-hand side. 1, 2, 3, 4, 5, 6 on the right-hand side. Now it could be that we have 10 billion atoms on the left-hand side when we start off the reaction, but then there will be 10 billion atoms on the right-hand side. In other words, in the products when the reaction is finished. Now, another very, very important thing that we need to know is the 3 steps in any chemical reaction. The first step is that the chemical bonds of the reactants are broken when collisions between reactant particles are hard enough. In other words, they collide with enough energy. So the first thing that happens is that bonds are broken. And we talk about effective collisions because not all collisions between reactant molecules result in them breaking apart. It's like motor car accidents. Not all motor car accidents are equally damaging. Sometimes it's just a bumper bashing and the cars don't look very different to what they looked initially, but then a head-on collision will completely destroy the car. So the same is true here. In order for the bonds to be broken, the reactant molecules really need to hit each other very, very hard. And that's why very often in order for reactions to take place, we need to add heat. For instance, like with cooking, we need to add heat in order to be able to break the reactant particles apart. Next, and this is quite an abstract step, we will look at this in more detail at a later stage. A highly unstable substance is formed. It's called an activated complex. It's actually more than one substance. It's actually where the reactant molecules break up into their atoms, and these atoms don't stay like that for very long because they don't want to be on their own, and so very, very quickly they recombine and form new chemical bonds in the form of products. And what's also very important is that step one requires energy to be taken in, and step 3, energy is given out. Now, it seems quite abstract at the moment, and so we will represent this with pictures in the form of graphs, and then it will make a lot more sense. And we will do this in the second video in this video series on chemical reactions.